Hello class, I would assume that you have already watched our previous videos on the principles of how our operations in matrices do work, and what we are going to have in this discussion would be some more examples in order for you to at least understand or master how the operations work. Starting off with the parts of matrix. For a matrix, all the elements or all those numbers that you see would be placed in a bracket. Okay, these two brackets would show that you are dealing with a matrix. For this matrix, you would find there different rows and different columns. So in here, you would have 2, 3, 4 rows and 1, 2, 3 columns. In order for us to designate this matrix, your M would be where you are going to place your rows, N would be for the columns. So in this case, you would have there 4 rows by 3 columns. The matrix would have a letter name, which would usually be placed in a capital letter. Inside would be smaller letter. Take the case of our elements. Inside would be what we call your elements or entries. Zooming it out, in each entry or in each element, it would have its own designation. Both of these numbers that you see as subscripts are called your index, whereby the first one would be your row index. The second one would be your column index. Either it would be called like A11 or A11. In case we would have K, what would be the index for element with the value of K? That would be taken as the element, counting on 1, 2, 3, 4 rows, 1, 2, 3 columns. So K would be the value for element 4, 3. In here, you would see a set of matrices, A until E, wherein we are required to do different operations. Let's work with requirement letter A. It says that we are going to have matrix A added to matrix B. Let's check matrix A. Elements would have 1, 3, 5 for the first column, 2, 4, 6 for its second column. With matrix B being 1, 3, 5, 7, 9, 0 for its elements. The primary condition in order for us to do our addition or subtraction of matrices would be to check if they are equal. What do we mean by equal matrices? Equal matrices would have the same number of rows with the same number of columns. So for our matrix A, we have there our designation for the size as the row multiplied by the column or 3 by 2 matrix. For matrix B, we have 2 rows by 3 columns. Checking on them, they are unequal. So requirement A, or that would be matrix A plus B, would be having no solution. Moving on to letter B. We are asked to work with matrix B less matrix D. So let's check matrix B. We have 1, 3, 5 for the first, 7, 9, 0 for the second row. This would be subtracted with matrix D having these elements. Checking on their size, we would find matrix B as having 2 by 3, matrix D also has 2 by 3 matrix. Now, we can work with our subtraction because they are equal matrices. In subtraction or addition, you are going to add or subtract elements with the same index. So in this case, your element 1, 1 would just be subtracted with element 1, 1 for the other matrix. Element 1, 2 would also be the same, subtracted with that element 1, 2 of matrix D. So to simplify, we would have B minus D to be equal to 1 less 4 for A11, 3 less 0 for A12, 5 less 1, A13, 7 less 1 for A21, 9 take away 2 for the next element, and lastly 0 take away 4 for our last element. Then we can simplify. 1 minus 4 would be negative 3, 3 minus 0 is 3, 5 minus 1 is 4. And then 7 less 1 is 6, 9 less 2 is 7, and 0 less 4 is negative 4. Moving on to letter C, the third requirement, we are asked to work with matrix A multiplied with matrix C. So let's copy matrix A. And have matrix C. How are we going to check if these matrices are compatible or can they be multiplied? The rule for multiplication would be to check if matrices are compatible. Take note that this is not equivalence, but then this is going to be compatibility of matrix. Let's move on checking on the size of matrix A. We do have 3 by 2. For matrix C, we have 3 by 3. Compatibility would have the same number or values for one row of the other matrix to the one column of the next matrix. That would be taken checking on these two values. Since in this example, we would have 2, which isn't equal to 3, then we can say that for letter C, we are not going to have any solution. Check on if we invert instead of A to C, we look for the matrix of C multiplied by A. So let's have matrix C and matrix A. This time, check on its size and look for compatibility. In this case, you would have 3 for the rows of the second matrix, 3 for the columns of the first matrix, which would mean that they are compatible. We can move on and have the multiplication of our matrices C and A. Although it would be easy for us to work with our multiplication of matrices with them having it in a horizontal manner, it would be easier for you guys to work on it if we would be arranging our matrices. What do I mean? So for matrix C, we are going to have it at such a spot this would be multiplied by matrix A, arranged correspondingly. So why do we have to do this? It is in order for us to check on intersections when we are filling up all of the resulting matrices elements. What do I mean? Let's work with our resulting matrix. That would be matrix CA. Start off with our first row and the first column. That would give us 4 times 1 plus 7 times 3 plus 0 times 5. Moving on to our second row. We would have 5 times 1 plus 8 times 3 plus 5 times 5. For the third row, 2 times 1 plus 1 times 3 plus 6 times 5. And that would be for the first column. Let's continue doing it for the second column. We would start with the first row, and this would be 4 times 2 plus 7 times 4 plus 0 times 6, or simply 0. The second column, we would have 5 times 2 plus 8 times 4 plus 5 times 6. And lastly, take on our third row. That would give us 2 times 2 plus 1 times 4 plus 6 times 6. We're going to be simplifying everything, and that would be the answer. So 4 plus 21, 25 plus 0 would be 25. Next, 5 plus 24, 29 plus 25 would be 54. 2 plus 3 is 5 plus 30 is 35. Next, 8 plus 28 would give us 36. 10 plus 32 plus 30 is 72. 4 plus 4 plus 36 would be 44. And this is the answer for requirement D. Requirement letter E would be similar with the previous requirements of operations. So, let's get the matrix resultant of A times B plus C. Start with A times B. So we have matrix A. This would be multiplied by matrix B. So we do the check. Our size would be 3 by 2 for the first, and matrix B would have 2 by 3. Since the column of the first and the row of the second would match, then we can move ahead and find the solution. Let's arrange A. And P. Take the first column with the first row. So that would be 1 times 1 plus 2 times 7. For the second, we have 3 times 1 plus 4 times 7. And for the third, take 5 times 1 plus 6 times 7. Now, how about for our second row? We have 1 times 3 plus 2 times 9. Moving on to the second row, 3 times 3 plus 4 times 9. And for the third, we would get 5 times 3 plus 6 times 9. Then we are done with the 2 columns. Moving on to our third row or column. Starting off again with our first row, 1 times 5 plus 0. Now for the second, we would have 3 times 5 and again 0, or that would be 4 times 0. For our third row, 5 times 5 plus 6 times 0, or again 0. So we can simplify our answer with the matrix 1 plus 14 3 plus 28 would give us 31. Then next, 5 times 42 would give us 47. Next one, 3 plus 18 would be 21. 9 plus 36 is 45. 15 plus 54 would give us 69. Then that's going to be 5, 15, and 25. This would be our resulting matrix for A times B. Now add C. our C would have the elements and 2, 1, 6. For adding, remember that what you are going to get would be those with the same index. In this case, we would have 15 plus 4 is 19. 21 plus 7 would be 28. 5 plus 0 is just still 5. Next row, 31 plus 5 would be 36. 45 plus 8 gives us 53. 15 plus 5 is 20. Last one, 47 plus 2 is 49. 69 plus 1 would be 70. 25 plus 6 is 31. And that would be the answer for requirement E. Now, how about requirement F? It's asking us to multiply matrix C and E, but take note that C would have to be taken as the transpose matrix. How do we do the transpose matrix? Transposing our elements within a matrix would only mean that those rows would have to be formed into your columns. For matrix C, its transpose would then be taken as 4, 7, 0 for the first row. This time it's going to be the first column. Next, we have 5, 8, 5 as its original second row. This time would be the second column. Lastly, 2, 1, and 6 are the elements of its third row, now the third column. Multiply these with our matrix E. So, let's work with our arrangement. The same procedure. Start off with the first column and the first row. This would give 4 times 1 plus 5 times 2 plus 2 times 2. For the second, we would have 7 times 1 plus 8 times 2 plus 1 times 2. The third would be 0 times 1 or 0 plus 5 times 2 plus 6 times 2. Let's move our next row. Still moving up to the first row, this time with the second column. That would give us 4 times 3 plus 5 times 0 or 0 plus 2 times 1. Next we have second row giving us the values 7 times 3 plus 8 times 0 or 0 plus 1 times 1. And for our third row, that would be 0 times 3 or 0 plus 5 times 0 or 0 plus 6 times 1. And that would be for our second column. Now, how about for our third column? Starting off with the first row, then we would have 4 times 0 is 0, plus 5 times 1, plus 2 times 2. Next row, we would have 7 times 0 or 0, plus 8 times 1, plus 1 times 2. And lastly, moving up to our last row, that would give us 0 times 0 or 0, plus 5 times 1, plus 6 times 2. So checking on to our simplified version of transpose of C multiplied by matrix E, we get 4, 14, 18. Seven plus 16, 23, plus 2, 25. 10 plus 12 gives us 22. For the second column, 12 plus 0 plus 2 would give us 14. 21 plus 1 would be 22. And 0 plus 0 plus 6 simply be 6. Next one, third column, 5 plus 4 gives us 9. 8 plus 2 is 10. And 5 plus 12 would be 17. This would be the resulting matrix for transpose of C multiplied by E. Requirement G is taking the cofactor of matrix E. It is denoted by having a subscript I and J. Cofactor would be the method used when we are going to solve the determinants of a matrix. In our case, the cofactor of E would be taken as our value, which would be placed into a determinant form given as a bar. Again, this bar would show that we are going to get the determinant. In case we are taking the cofactor of element 1, 1, we would have the values of the remaining elements not eliminated. So that would be 0, 1, 1, and 2. This whole set of numbers are what you call your minors. The resultant element would be what we call our cofactor. Now let's take our cofactor. The cofactor of matrix E would be taken as the remaining elements, or that would be the minors. So starting with element A, 1, 1, the minors are taken as the determinant of 0, 1, 1, 2. For the next element, you would have 2, 1, 2, 2. These are such values. How about the next element? Eliminating the third column, we would have our values or minors 2, 0, 2, 1. And we are done with the first row. Moving on to our second column, taking the second row, taking the first column. Our minors are taking us 3, 0, 1, 2. For the second row, we would have 1, 0, 2, 2. And lastly, for the third row, our values are taken as 1, 3, 2, 1. For the last row, start with the first column. We would have 3, 0, 0, 1. For the second column, we get 1, 0, 2, 1. For the third element, remaining minors are 1, 3, 2, 0. Okay, before we are going to get the determinants, what we would have to do, and don't forget that we are supposed to be interchanging signs. For the first column, we are going to have A11 as positive. The others would be negative for the first row. For the second row, we would have it interchanged as negative, positive, and negative. The third row would have positive, negative, and positive. And we are ready to take our determinants. For the determinants, we are going to get our diagonals going down as positive, going up as negative. In this case, we would have 0 times 2 minus 1 times 1. That would be negative 1. Next, 2 times 2 minus 2 times 1, or 2. Take note that there would be the negative sign, so this would turn out as negative 2. Thirdly, 2 times 1 is 2, minus 0, still 2. For the second row, we would have 3 times 2 is 6, minus 0, positive 6. Take the sign outside, making it negative 6. 1 times 2 is 2, minus 0 would still remain as 2, positive. Next one, 1 times 1 minus 2 times 3, or 6, would give us 5, negative, and another negative, giving us positive 5. 3 times 1 is 3, minus 0 is still 3, positive. 1 times 1 minus 0 would still be 1, taking it as the negative. And 1 times 0 minus 6 would give us negative 6. And this would be our cofactor of matrix E. Now let's take the adjoint of a matrix. The adjoint of a matrix would also be known as the adjugate. So adjoint C is the same when you would find in other references adjugate C. What would be our formula? Adjoint C would be taken as a cofactor with its transpose. So for matrix C, take the cofactor first. Starting off with first row, first column, we would have the remaining minors, 8, 5, 1, 6. For the second, we would have 5 and 5, 2 and 6. And for the third, the remaining elements would be 5 and 8, 2 and 1. And that would be for our first row. For the second row, do the same. our elements would be split. That would be 7 and 0, 1 and 6. Second column, we have 4 and 0, 2 and 6. And for the third column, we are left with 4, 7, 2 and 1. Now for our last row, starting with first column, we would have our elements 7, 0, 8, 5. With the second column, we are left with 4, 0, 5, 5. And finally, for the last column, we would get 4, 7, 5, 8. Take the determinants of these minors. So the cofactor would turn out as don't forget that we would have our negatives for the interchanging signs, starting off with 48 minus 5 is 43. 30 minus 10 is 20. 5 minus 16 is negative 11. Next, 42 minus 0 is still 42. 24 minus 0 is 24. By the way, there would be a negative sign here. Thirdly, 4 minus 14 is negative 10. Add the negative, so positive 10. 35 minus 0 stays 35. 20 minus 0 is 20 plus the negative. And lastly, 32 minus 35 is negative 3. Now that we have our cofactor, take its transpose. And again, that would simply be turning all the columns into rows. So that would be 43, 20, negative 11, negative 42, 24, and positive 10. Lastly, 35, negative 20, and negative 3. So this is the adjoint of matrix C. So next, taking on our inverse of matrix F. For our matrix F inverses, what we would have to do would be to follow a formula. That formula is given as inverse of matrix as the reciprocal of the determinant of the matrix multiplied by its cofactor, which is reversed. So in order for us to start with our matrix inversion, take our determinant of matrix F first. Copying our matrix, then we can work with our short method solutions, or that would be like taking our Sarus method, or in this case, we work with our butterfly method. Start with the positives. So this is given as 4 times 0 times 2 would be 0. And another plus 2 times 3 times 1 plus 0 times 1 times 2, or another 0. So this would give us 6. Now, how about for our negatives? Take the diagonal going upwards. That would be 1 times 0 as 0, minus 4 times 2 times 3, another minus 2 times 1 times 2. So if we convert, or if we simplify, we have here negative 24 minus 4, giving us negative 28. So our determinant is taken as 6 minus 28, or that would be negative 22. Done with our determinants, next we are going to get our cofactor. So starting with our, or let's just simplify it and squeeze our answer here. Start with our first row, first element. What we have would turn out as 0 minus 2, 0 times 2 minus 2 times 3, or that is 6. So minus 6. Next one. We're going to have 1 times 2 minus 1 times 3, or negative 1. Third element, 1 times 2 minus 0, or 2. We also take the other elements. Now continuing with our second row, first element. So this would be 2 times 2, or 4, minus 0. Then let's take the next. 4 times 2 is 8, minus 0. And last, for second row, we have 4 times 2, or 8, minus 2. Let's finish our cofactor by working with our third row, which would give us 2 times 3 is 6, less 0. This is still going to remain as 6. Next, we have 4 times 2 is 12, minus 0. And lastly, we would have 4 times 0 is 0, minus 2. And that would be for our partial cofactor, because we would still have to work with our signs. So we are going to have this as positive for the first element, negative for the second element, making it positive 1, and positive for the third element. Then for the second row, we would have negative, positive, negative. Third row, positive, negative, positive. Then the next thing would be to work with our reverse. in order for us to reverse our matrix, we are going to keep our diagonal just the same. So that would give us -6, 8, and -2. The others would have to take each other's places. So working with the first two, that would be +1 and -4. So +1 goes down, -4 would stay up. Next would be our pair of 2 and 6. 2 stays down, 6 goes up. And lastly, we would have -6 and -12. And that would be for our reverse. The next thing that we are going to work on would just be plugging in all of the parameters into our formula. So we said that our inverse of matrix F would just be our determinant's reciprocal, or that's going to be 1 all over -22, multiplied by our matrix. You can leave it as is if you would like our scalar to be outside, or you can also integrate in order for us to give, let's say, just one matrix. This would be equal to integrating our 1 all over -22 into our matrix. So either you are going to work with the scalar or our determinant out, or just integrating it into the matrix. Now let's check if our inverse of matrix F is correct. How do we do that? We are going to get the property stating that if we are going to multiply the inverse of the matrix by itself, or the original matrix, what we are going to have would be an identity matrix. Identity matrix, as you have known, would be that matrix where the diagonal would be identical, or that would be with the value of 1, and all the other elements would be given as 0. So let's check. Our original matrix is given as and this would be multiplied by our inverse. In order for us to multiply our matrices, it would be best if we are going to have them arranged. So let's just arrange our first matrix for the row. Then for our second matrix, So let's check. First, we're going to work with our first row, with the first column, which would give us 4 times 3/11 minus 2 times 1/22 minus 0. For our second row, we would have 1 times 3/11 plus 0 minus 3 times 1/11. Let's check on the third row. We would have 3/11 minus 2 times 1/22 minus 2 all over 11. How about for the next row or the next column? For the first row, we would have 4 times 2/11 minus 2 times 4/11 minus 0. Second row, we would have 1 times 2/11 minus 0 plus 3 times 3/11. That would be 9/11. For the last row, 1 times 2/11 minus 2 times 4/11 or 8/11 plus 2 times 3/11 or 6/11. Let's place here the 1. Moving on to our last column, starting with our first row, we would have negative 4 times negative 3 would be negative 12/11 plus 2 times 6 would be 12/11 plus 0. Next, we would have 1 times 3/11 and that is negative, plus 0 times 6/11 plus 3 times 1/11. And lastly, take the last row. 1 times negative 3/11 would still be the same negative 3/11 plus 2 times 6 would be 12/11 plus 2 times 1, 2/11. And this would complete our matrix. Simplifying, we are supposed to arrive with our identity matrix. So let's check. 12/11 minus 2/11, 2/22 or 1/11. So this would turn out as 1/11 would give us 11/11 or that would be 1. Below it, 3/11 plus 0 minus 3/11 would still be 0. Thirdly, 3/11 minus, again, this would be taken as 1/11 minus 2/11 would also be 0. For the second column, 8/11 less 8/11 would be 0. 2/11 minus 0 plus 9/11 would be 11/11 or 1. And 2/11 minus 8/11 plus 6/11 would be canceling out each other, giving us 0. For the third column, negative 12 plus 12 elevenths would be giving us 0. Negative 3 plus 0 plus 3 would still be 0. And negative 3 plus 12 would be 9 plus 2 would be 11 elevenths, or that would be 1. So it shows that our inverse of matrix F is correct.